I hope you are enjoying sessions with us and you are learning and trying to become better and better every day. That is how human minds develop. Okay, so let's get started with today's lecture. So in the previous lecture we did some basic level solving and advanced level solving on chemical kinetics and one question on solution. So today we are going to talk about different types of solutions and we are going to start with the second portion of the chapter, that is colligative properties. So let's start with the lecture. Okay. So till now we have understood the concept of vapor pressure and how vapor pressure changes when we add a non-volatile solute. Okay. Now in today's lecture we are going to talk about solutions and its different kind of solutions that exist and how are the parameters for these solutions set. Okay. So now let us look at a solution. So we know that solution is basically mixture of two components. Suppose A is your solvent and to this you are adding B. Okay. So suppose in a container we are having a solvent A. Okay. So we are having a solvent A. Okay. Now we are adding a solute. Say we are adding a solute. Okay. So let me make something like this. So we are having a container that contains solute. Okay. So we are having another container that contains, okay, say some other solution, okay, that is B. Okay. It can be solute, it can be another solution only. Okay. Another solvent also. So we know that there are two solutions, A and B. Okay. Hope this is clear to everyone. Now let us call this as solute. Okay. Now if we look at only the solvent system, just like the way we were studying in gases, that gases are of two types, ideal and real gases. Ideal is just a hypothetical condition. Whatever gases are there in nature, they are real. Okay. So similar is the concept with solution also. Okay. So we'll say that solution is also of two types. One is ideal solution and non-ideal solutions. Okay, or also called as real solution. So if you look at the just solvent A or the like component A, okay, or the liquid A, so better is we name this as liquid A. Okay. So this is a liquid A and suppose this is your liquid B. Okay. It can be a solvent solute also, so no need to worry about that. So we are saying that we are having two liquid A and B in a container. Now just look at this container A. In this we are having only one component, okay, that is A. So the interaction that would be happening inside this container would be interaction between the similar molecule, that is A. Okay. So we'll say that because only one liquid is present, so it will have only one kind of interaction, that is A molecules of liquid would interact with A molecules of that same liquid. Okay. So in this we will say that we are having AA type of interaction. Now suppose this is another liquid B. Okay. Now if you look in this, we are having only one component, so the interaction possible is only that of B and B. Okay. Now when we mix both of these solutions, okay, we mix them in the common container. So we are mixing them in a common container. Okay, so now you can guess what kind of interactions would be possible in this. So we have formed a homogeneous solution of two liquids A and B. So now this basically contains, okay, two liquids A and B. So we can call this as a solution of two liquids A and B. Okay. Now when you look in this container, we have two different type of molecules. One is A and the other is B. So the basic interaction that would be present in them would be, okay, A molecule would still interact with another A molecule. Similarly, B molecule would interact with another B molecule, and there would be one new interaction that would be happening between them, is the interaction between A and B molecule. So these are the basic interactions that are happening in this solution containing two components of A and B. Okay. So we know that initially only liquid A was there, so there was only one kind of interaction that was possible, that was between A and A, okay. And in the second container, liquid B was present, so only one interaction was possible, that is between B and B. Now when we mix them in the common container, so we'll say that the new interactions possible is AA, okay, A interacting with A, B interacting with B, and now a new interaction in which A is interacting with B. So based on these kind of interactions, we can classify the solutions into ideal or real solutions, okay. Now because we have, what we have done over here is, we have mixed two solution, okay. So we can say that we have done the mixing of two solution, okay. So we know that whenever we are mixing the two solution, it will be a irreversible process, okay. Generally it is a irreversible process and it is a spontaneous process. So we know that delta G mixing would be negative because it is a spontaneous process. When you mix two substances, they mix together. So that is a spontaneous process. So delta G would be negative. Now if you look at the delta S mixture, can we comment anything about the delta S mixture? Now we'll say that because the total volume has increased, right, because we have mixed the two solution, the total volume of the solution has increased. And we know that entropy is basically nothing, it is the degree of randomness. So if you look at one of the molecules, say let us look at the A molecule or the liquid A. Liquid A will have A molecules. Now that one A molecule will have a larger volume to move because the overall volume has increased. So when we are mixing the two solution, the volume has increased. So if you look at the one molecule, so one molecule will have more free space to move, so that the randomness would increase. Similarly for the other molecule B, because a molecule B would have more volume or more free space to move, so it will have also more degree of randomness. So when you mix two liquids, we will say that the total number of particles is increasing, okay, and also the total volume is also increasing. Because the total number of particles has increased, so more is the number of particle, more would be the randomness, and because the total volume has increased, so the space available for one molecule to move would increase. So its degree of randomness would also increase. So we'll say that the thermodynamic property would be delta G mix is negative and delta S mix is positive. So if you look at the formula, delta G is basically given by, okay, so this is not there in the syllabus, but we have derived this in the gaseous state chapter, so we can directly say that delta G would be minus 2.303 N total, okay, into R is your gas constant, T is the temperature, into summation of Xi ln Xi. Okay, how we derive this? Just it is basic thermodynamic, okay, so we can derive this, but if you have done it, then it's good. If you have not done it, you can just memorize the formula for the time being, okay. So delta S mix would be, sorry, this is plus 2.303 N total RT summation of Xi ln Xi. Delta S mix would be minus 2.303 N total into R into T into summation of Xi ln Xi. So Xi is the mole fraction, okay. Now you can, because we are writing, we have to write over here ln, we have to write log over here because we have already taken 2.303 factor, okay. So this would be Xi summation of log of Xi, Xi summation of log of Xi, okay. So this you can directly use to find the delta G mixing and delta S mixing of the solution, okay. So suppose we are having Na moles of A, okay, Nb moles of B, so we'll say that the mole fraction of A would be Na upon Na plus Nb, and the mole fraction of B would be Nb upon Na plus Nb, okay. So if in a question we have been asked, temperature has been given to us, the value of R generally we will take it as 8.314 because we want delta G and delta S to come in joules. So we'll just 2.303 N total. N total is basically Na plus Nb, okay, the sum of the moles of all the component, into R, that is gas constant into temperature into summation of xi, because there are two components over here. So the formula would become 2.303 N total RT into XA ln XA plus XB ln XB. Okay. Similarly, delta S mix would become minus 2.303 NR. This is not T term, is not over here. So this is N total R summation of XI, or minus 2.303 N total into R into XA log XA plus XB into log XB. Okay. So in that way you can get the value of delta G and delta S. So you can see that because X is always less than 1, so log of any quantity which is less than 1 would be negative. So there will be negative term coming from this, because this is overall positive, so this will become negative. Now this already has a negative charge, and log of anything that is less than 1 will always give us a negative value. So when you multiply this, we'll get delta S as positive. So this is the basic formula of delta G mixing and delta S mixing. Okay. Hope this is clear to everyone. You can just write it. Okay, so what we can say is, there was initially liquid A in which only A interaction was possible. There was another liquid B in which only BB interaction was possible. Now when we mix them, so what would happen? The surrounding of each molecule would change. There would be some A interactions, and there would be some BB interaction, and there would be some AB interaction. So initially what was there? A molecule was surrounded by A molecule only. Okay, so the A molecule was surrounded symmetrically by A molecule. In this liquid, the B molecule was symmetrically surrounded by B molecule. Okay. Now when we mix them, so what will happen? Some A molecule would be surrounded by some B molecule as well as A molecule, whereas some B molecule would be surrounded by some A molecule as well as some B molecule. Okay. So what is happening? The environment of one molecule is changing, because initially the environment was different, only the similar molecules were near them, and in the other solution only similar molecules was near to a molecule, but in the final solution a molecule would be surrounded by a different molecule as well. So we'll say that the environment of that particular molecule has changed, because instead of A, now some B molecule has also come. Similarly for the B, we'll say that instead of B, which is surrounding the B, some A molecule has also come. Okay. So based on these interactions between AB, okay, we'll decide whether the solution is ideal or non-ideal. Okay. I hope you have written this. Okay. So just let me erase this now. So now let us look. Now what is an ideal solution? Now when we have mixed two solutions, say liquid A and liquid B, the surrounding of A and the surrounding of B has changed. Okay. Now like a shell of B as well as A is formed near a molecule. Similarly, shell of A and B are formed near the B molecule. Now ideal solution is a solution when two components are mixed together, if the surrounding does not change much or the surrounding remains the same as that of initial, we will call those solutions as ideal solutions. That means whatever kind of interaction was happening between A and whatever kind of interaction was happening between B and B, now the new interaction that would be there between A and B, they are all same. So it's like, common example which we can take is, suppose I am surrounded by some like-minded people. Okay. Suppose I am surrounded by people like me only, who thinks like me, whose like talking tone is similar to me, whose behavior is same to me, like whose height, whose physique is similar to me. Okay. Suppose he is in the other room. Okay. I am one molecule. So say 50 molecules like me are present in this room, and in the other room we will say that 50 type of that molecule which resembles lot like me is present in the another room. Now when we mix them both, okay, when we mix both the molecules, so I will be surrounded by that molecule also, okay, but because that molecule resembles a lot like me, so my interaction would be with him would be the same as that which was with the other same molecule which was present in the room initially. Okay. So in this case we will say that upon addition of the new component, the interaction didn't change. That means the environment around me didn't change. Like like you might have faced, everyone might have faced this thing, like when we go to say when we are like a very small kid, when we are first going to the school, so we have a set environment at our home. Okay, so we are like very small, we are just 3 to 4 years old, so we are set with our environment. Okay, there are some parents, okay, there are some parents, okay, there are some siblings present. Okay, so in that case what happens is our interaction with them is like similar, because all of them are loving, all of them are caring, so our interaction with them is similar. But when we go to a school, the first time when we go to a school, when we step inside the school, if you can remember, I can remember, like I was crying like a hell. I didn't want to leave my mom, I didn't want to come outside my house. So that was because my environment changed, the people around me changed. Okay, so then interactions, the new interaction would be like me and my teachers or the other students or the other friends who were sitting over there. So because of that change in environment, there was a change in interaction. Okay, but suppose I was in first class, second, third, fourth, 9th, 10th, 11th. Now suppose from 11th I am going to 12th. Now if you will imagine that like you are surrounded by the same people only, same kind of people only. So when you step in your new class, say in the 12th class from 11th class, your surrounding does not change much. Okay, now the interaction that was there initially, okay, even if some new students come in your class, the interaction would remain the same. So such kind of interactions or such kind of solutions where upon addition of the other component, the interaction doesn't change much and the environment doesn't change much, they are called as ideal solutions. So the first and the foremost point is, in an ideal solution we say that all the type of interactions are same. Okay, so all the type of interactions are same. That is, AA interaction is same as that of BB and BB interaction is same as that of AB. Okay, so these kind of solutions where mixing of two liquid doesn't have any new type of interaction or their environment remains the same, their basic interactions remain the same, just when they were in the, just like when they were in the pure state. Okay, so such kind of solutions are called as ideal solutions. Okay, now if you look at the ideal solution, because the interactions has not changed, no new bonds is formed, no new type of interaction is present, the interactions were similar to that of the original liquids, the pure liquids. So we'll say that delta H, change in energy or change in enthalpy for such solution would be 0. Okay, and we'll also say that delta V mixing would be equal to 0. Okay, hope this is clear to everyone. Now one very important point is, ideal solutions always obeys Raoult's law at every range of concentration. So we defined ideal solutions as those solutions which will always obey the Raoult's law. Okay, and we'll also say that the different kind of interactions are same, the delta H mix and delta V mixing is also 0. The fourth thing which we'll say that if we are mixing two components, then delta G mix would be plus 2.303 N total into R into T XA log XA plus XB log of XB. Okay. Similarly, if I want to find the delta S mixing, so delta S mixing I know would be minus 2.303 N total RT XA log XA plus XB log XB. Okay, hope this is clear to everyone. So we'll say that suppose we are mixing 10 ml of liquid A with 10 ml of liquid B. Okay, because the interactions are same, so after mixing we'll get 20 ml solution. Okay, so we are expecting that on mixing 10 and 10 ml solution we should get 20 ml solution, and actually when we mix them we got only 20 ml solution. So we'll say that the change in volume is also 0. Okay, now this is little confusing. When I was studying this in my school days, so like I could always say that whenever I am mixing 10 ml with 10 ml other solution, so always it will be 20 ml form. But from this chapter I understood that it can be greater than 20, it can be less than 20. Only in the cases of ideal solutions we say that 10 ml when mixes with 10 ml give us 20 ml. So in all the questions which we are doing in the mole concept or ionic or chemical equilibrium thermodynamics, we assume that those solutions are ideal. Okay, so this is the basic ideal solution, you can write it down. So ideal solutions are those solutions which obeys Raoult's law at all concentration. The interaction between AA, BB and AB would be same. Because the interactions are same, the environment has not changed and there would be no change in the overall enthalpy. So delta H mixing would be 0, delta V mixing is also 0, indicating that when we are mixing two components, the total volume would be just the sum of the individual volumes. And we know that delta G mix will always be negative, okay, because it is a spontaneous process, and delta S will always be positive because it is a spontaneous process, and these are the formula to calculate. Okay, so just write it down quickly. Okay, so we'll say that because delta H is equals to 0, when we are mixing these solutions, these two liquids to form a solution, we'll say that neither heat is released nor heat is absorbed, okay, during dissolution of these two liquids. Okay, so hope you have written this now. So we have already said that AA, AB, BB interaction should be same, that is A and B are identical in shape, size and character. Okay. So the examples, now examples are important. So if we mix benzene with toluene, benzene is basically C6H6, toluene is a methyl group attached to benzene. Both of them are almost similar, okay, they are non-polar, sizes are similar, okay, character is also similar, so they will form ideal solution. N-hexane, N-heptane, okay, N-hexane is having 6 carbon, N-heptane is having 5 carbon, only the number of carbon is different, else the size, okay, the shape, the character would be the same. Similarly, chlorobenzene and bromobenzene, okay, similarly ethyl chloride and ethyl iodide, N-butyl chloride, N-butyl bromide, CCl4, SiCl4, chlorobenzene, bromobenzene, bromoethane and chloroethane. Okay, so all of them are ideal solution. So you can easily memorize them because you can see that examples are very typical. Basically, the two molecules are of the same character. Okay, both of them are either non-polar or both of them like have similar structure. Okay, just number of carbon, one carbon is different. So this is benzene, toluene, heptane, hexane, chlorobenzene, bromobenzene, ethyl bromide, ethyl iodide, N-butyl chloride, N-butyl bromide, CCl4, SiCl4, chlorobenzene, bromobenzene, bromoethane and bromomethane and chloromethane. Okay, so we'll say that they are following Raoult's law. So the graph would be something like this. We have already drawn this in the previous lecture, that is vapor pressure versus mole fraction. We'll say that mole fraction of A is 1 over here. So mole fraction of XB would be 0 over here and XB would be 1. So suppose this is the partial pressure of P over A, because when XA is 1 only one component is present, so that it will be P naught A. When XB is 1 it means only B is present. Okay, so if we look at the Raoult's line, so we'll say that if we draw the Raoult's line for the individual component, so this would be the Raoult's line for the A component, Raoult's line for the B component, and if we want to have the total, so total will be this. Okay. So I have already told this to you and we have already done some questions on this. So if we want to plot both liquid and vapor phase together, okay, so we know that at very high pressure, because at very high pressure molecules would be close to each other, so in that case only liquid will be stable state and at very low pressure vapor would be the stable state. Okay, so this was the total pressure. Okay, and if you draw the that of vapor curve, so vapor curve was something like this. So I have already told you this represent the curved line represent the vaporous phase, and the liquid and the straight line represent the liquidous curve. Okay, and the region between them is representing equilibrium between liquid and vapor. We have already done some questions on this, dew point, bubble point. Okay, so we have already discussed this in detail. Now suppose if we want to convert this into a temperature versus mole fraction curve. Okay, so suppose this was PB, P naught B, and this is P naught A. Okay, so if we want to convert this into a temperature versus mole fraction curve, okay, so let me draw the temperature versus mole fraction curve. Okay, now we know that now XA was 0 over here and XA is 1 over here. Similarly, when XA is 1, that means XB is 0 and XP would be 1 over here. Okay, so we know that because out of A and B, A was having more partial pressure. That means A was more volatile, okay, and B was having less vapor pressure. That means B is less volatile. Now, the boiling point of the two liquids A and B, which will have more boiling point, a more volatile liquid will obviously have less boiling point. We define boiling point, normal boiling point, as the temperature, okay, the normal boiling point, you can write it down as well. This is a very important definition. So, normal boiling point of a liquid is the temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure, that is 1 atm. Okay, so we say that the boiling point of pure water at 1 atm is 100 degrees Celsius, because if you keep on changing the external pressure, the boiling point would also change. So, the normal boiling point is the temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure, that is 1 atm. Okay. Now, because we know that A is having more vapor pressure, that means it has to be heated less, because already its vapor pressure was more. So, if we heat very small quantity of heat if we supply to it, so it will form the corresponding vapor, so that the total vapor pressure becomes equal to the atmospheric pressure. So, its boiling point would be less. But if the vapor pressure is less, it means that we have to heat it enough so that the vapor pressure becomes equal to the total atmospheric pressure. Okay. So, we will say that the liquid which is having higher vapor pressure will always have lower boiling point. So, T naught A will be over here and T naught B will be over here. Okay. So, I hope this is clear to everyone. Now, we already know that the dependence between pressure, vapor pressure and temperature is given by Clausius-Clapeyron equation, which was saying us that ln P2 by P1 is equal to delta H vaporization upon R into 1 by T1 minus 1 by T2. Okay. So, this was the Clausius-Clapeyron equation, which was giving us the relationship between the pressure, the vapor pressure and the temperature. Okay. So, when you draw like this curve on temperature versus composition axis, so the graph comes something like this. Okay. So, the graph comes something like this. Okay. At high temperature, which phase will be stable? When you heat anything, we know that its vapor are formed. So, we will say that at high temperature, vapors are stable. So, at high temperature, vapor would be there, and at low temperature, liquid would be there. Okay. And the area between, the region between the two graphs would represent the equilibrium between liquid and vapor. Okay. So, this is your vaporous curve, this is your liquidous curve, and the region between them represents liquid versus vapor curve. So, this is the transformation of this graph into temperature versus mole fraction graph. Okay. So, just write it down. So, this is important, because we will study distillation of ideal solutions through this graph. Hope this is clear to everyone. Okay. Examples are very important. Questions are directly asked on examples. They will ask like benzene and toluene, which of the following properties is true for benzene and toluene mixture? Delta H equals to 0, delta H is equals to positive, delta H is equals to negative, or say delta G is positive. So, answer would be delta G equals to 0. So, you need to know the examples. So, same kind of molecule, non-polar molecules are basically having no interactions between them, like the interactions which are present initially, the same kind of interaction, no new type of interaction is happening between A and B. So, we will say that type of solution is a ideal solution. Okay. So, hope you have drawn this graph as well now. Now, let us look at a real solution, or we'll call it as a non-ideal solution. When the interactions between the different liquid, that is the different molecule A and B, is not similar to that of the original pure component, that is interaction between AA and interaction between BB, then those kind of solutions would be called as real solutions. Real solutions have one thing in common, that they do not obey Raoult's law. Okay, so they will not obey Raoult's law. Okay, now there are two types of real solution, one which shows positive deviation from Raoult's law and the other which shows negative deviation from Raoult's law. To understand what is positive deviation and negative deviation, let me explain it through an example. Okay, suppose we were having in a container A, okay, in the container, the first container, suppose we are having liquid A, and in the other container we are having another liquid B. Okay, now in this container only A interaction was there, in this container only BB interaction was there. When we mixed it in the common container, so now a new interaction would be happening, that is between A and B. Okay, now suppose the interaction between A and B is not strong at all. Okay, the interaction between A and B are not strong at all. Rather, what they are doing, they are weakening the AA and BB interaction. So in that case, what would happen? Both A and B would easily escape out and form the vapor. So the vapor pressure exerted over the solution would be greater than what we were expecting from the Raoult's law. So we'll say that the vapor pressure has increased. So this is a positive deviation. Okay, let me take an example so that you understand it. Suppose we were having water molecule. Okay, I hope this is clear. Suppose we were having ethanol. Okay, ethanol is C2H5OH, and another container, say we were having carbon disulfide. Okay, carbon disulfide is a non-polar molecule. Ethanol is a polar molecule. Okay, now let us look at this ethanol container. What kind of interaction would be there in the ethanol container? Ethanol would be basically hydrogen bonded to another ethanol. Hydrogen bonding is basically the interaction of hydrogen already attached to a small electronegative atom with another electronegative atom. So we know that in ethanol a hydrogen is already attached to oxygen. Now this can interact with other oxygen of the other ethanol molecule. So there would be a hydrogen bonding between two ethanol. Okay, so we know that in this container there is a hydrogen bond between two ethanol molecules. So one ethanol is holding the other ethanol, and that ethanol is holding some other ethanol. So all of them are holding each other in remaining in the solution and not going outside as the vapor. Okay, it's just like that you are in your home, coronavirus is holding you from going outside, from escaping from your home. Okay, so we'll say that in this container the hydrogen bonding system was there, so ethanol was holding other ethanol through hydrogen bonding. In this, what was there? There was carbon disulfide, so there would be some dipole type of interaction, basically instantaneous dipole interactions would be there in this container. Now when we mixed both of them, so what would this carbon disulfide do? Because carbon disulfide itself was non-polar, it cannot interact with a polar molecule much effectively. So what it will do? It will come between the two ethanol molecule. Now the ethanol molecule was binded to each other through hydrogen bonding. Okay, now when we added carbon disulfide to it, so carbon disulfide would come between them. Okay, and they would allow the two ethanol to get separated from each other. Now when the two ethanol get separated from each other, so now both the ethanol molecule can easily escape because they are not holding each other in going outside. Okay, so more number of vapors of ethanol would be formed in that solution, and carbon disulfide is also going in the same manner because ethanol molecule would come in between the carbon disulfide interaction, and both the carbon disulfide molecule would be would not be attached to each other, and they would become free, and they can also leave and escape out as vapor. So the total vapor pressure over the solution would be increasing. So such kind of solutions is called as solution showing positive deviation from Raoult's law. So they do not obey Raoult's law. Okay, I hope this is clear to everyone. So we are talking about positive deviation from Raoult's law. Okay, so we'll say that they do not obey Raoult's law. All real solutions do not obey Raoult's law. The one very important factor over here is delta V mixing is greater than 0. Okay, I think this is easy to understand. Like पहले सिर्फ इथेनॉल था, इथेनॉल एक दूसरे के साथ हाइड्रोजन बॉन्डेड था, जब हमने उसके ऊपर एक और कंपोनेंट डाला तो दोनों इथेनॉल के हाइड्रोजन बॉन्ड टूट गया और वो दोनों दूर चले गए। जब वो दूर गए तो क्या हुआ, वॉल्यूम एक्सपैंड हो गया। ओके, सो वॉल्यूम इंक्रीज हो गया। सो सपोज इनिशियली 10 ml ऑफ इथेनॉल था एंड वी वर मिक्सिंग 10 ml of say carbon disulfide, we were expecting the volume to be 20 ml, but because the interaction between the liquids have broken and they have moved little far apart, so they will occupy more volume, okay, and the total volume would increase. So in that case I will say that delta V mixing is greater than 0. So volume is increased after dissolution, that is not equal to the volume of the summation of volume of individual components. Okay. Now similarly the second important property is delta H mix. Okay, this is also greater than 0, that means it is exothermic. Now what is happening? Ethanol was hydrogen bonded, so basically a molecule was bonded to each other through certain kind of bond, be it a van der Waals forces, be it a dipole forces, be it a hydrogen bonding. Now when we have added another component, this interaction has broken. So when that interaction has broken, the energy corresponding to that particular interaction would get released out, okay, in the form of energy. So we'll recover it in the form of energy. So we'll say that delta H is greater than 0, that it is a delta H is greater than 0, it is a endothermic process because a bond has been broken over there. Okay, so basically there was an interaction between A type of molecule, when you added another molecule B, so the interaction was broken. So basically for breaking this interaction, it would absorb some energy because bond cannot get broken by itself. So it absorbs some energy from the surrounding or from the system itself. So we'll say that it is basically an endothermic process, so delta H would be greater than 0. So we'll say that heat is absorbed in this case. Okay, delta G mixing is again less than 0. Okay, and delta S mixing is greater than 0. Okay, one important thing which we can say over here is, now when we have taken only AA and we have taken only BB, when we have mixed both of them, so we are saying that interaction between AB is weaker. Okay, AB is not interacting at all, the interaction between AB is weaker. What B is doing to A or what A is doing to B is breaking its interaction with the similar molecule. So we'll say that AB interaction is weaker than AA or BB interaction. Okay, hope this is clear to everyone. Okay, so we'll say that for a positive deviation solution, delta V mix is greater than 0, delta H mixing is greater than 0, indicating that it is a endothermic process. Delta G mix is less than 0, delta S mix is greater than 0, AB interaction is weaker than AA or BB interaction. So we can say that after addition of B to A or after addition of A to B, the escaping tendency of both A and B increases. Okay, so escaping tendency of both A and B has increased. Okay, due to which they will form more vapor and the vapor pressure would increase. Okay, hope this point is clear to you. So these kind of solutions are called as real solution. Okay, so just write it down quickly. So when you are mixing, suppose in initial container we had only A liquid, so we know that only A interaction was possible. Now that A interaction was holding both the A molecule from escaping out as vapor. Okay, because initially only A was present, so A was basically interacting with A and forming some kind of bond or interaction with other A, and in the process the two A was getting joined together through certain interactions, and due to which both the A were holding each other from escaping out of the solution into the vapor phase. Okay, now when we added B over it, so what happened, B came in between A and A, okay, and the interaction between AA weakened, due to which now A becomes free, the two A molecule becomes free and they can escape out as vapor, so the vapor pressure increases. Okay, similar thing happens with the B. Okay, BB was having the same certain kind of interaction, due to which one B was holding other B from going outside. when you added A over it, so A came between the two BB, okay, and the two B molecules interactions weakened, due to which the B molecule started to, okay, go out or escape out as vapor. So we'll say that more vapor of A and B are formed, that is escaping tendency of both A and B has increased. So basically A is diluting the strength of bond that was present between the molecule. Similarly, B is diluting the bond between AA. Okay. So if you look at the PA, so if you look at the vapor pressure exerted due to one component, now according to Raoult's law, PA was equal to P naught A into XA. But because this is not following the Raoult's law, okay, we know that the vapor pressure would increase. So we'll say that PA would be greater than that expected from the Raoult's law. Similarly, PB would be greater than that expected from Raoult's law. So we'll say that PT is greater than P naught A XA plus P naught B XB. Okay. So the pressure over the solution is greater than expected from that of Raoult's law. So that is why we are saying it is a positive deviation. Okay. Hope this is clear to everyone. So example could be, I have already told you, acetone and carbon disulfide. Acetone is basically having a, okay, acetone is basically this. So it is having a dipole. So one acetone would be interacting with other acetone. Okay. So they are basically a negative and they are having a dipole. So positive negative dipole would be there. So there would be interaction between two acetone through dipole interaction. Now when you add carbon disulfide to it, carbon disulfide will come in between them. It will weaken this interaction. Both of them will get free, and now both of them can escape from the solution into the vapor phase. So more number of vapor would be formed as expected from Raoult's law. So the pressure would be more. Similarly, acetone ethanol. Okay, ethanol was forming hydrogen bonding. Acetone itself was forming a dipole. When you added ethanol over acetone, so acetone would come in between ethanol. The hydrogen bond between ethanol would be disrupted, and the ethanol would become free and would escape out easily. Similarly, the acetone molecule was having interaction between them. When you have added ethanol, so ethanol would come in between them, okay, and the interaction between the acetone molecule would weaken, due to which the acetone molecule can easily escape out of the solution in the vapor phase. So the vapor pressure would increase. Similar example is water methanol, water ethanol, CCl4 toluene, CCl4 chloroform, acetone benzene, CCl4 methanol, chlorohexane and ethanol. So this is again easy to predict. Ethanol having hydrogen bond, okay, cyclohexane added, it breaks the hydrogen bond, both the molecule becomes free. Methanol having hydrogen bond, CCl4 non-polar molecule, when you add to this, the interaction between methanol will break, okay, and the methanol will become free to escape. Acetone, okay, so acetone was basically a polar molecule, benzene is a non-polar molecule, okay, so acetone when you add it to benzene, so the interaction between the acetone would weaken because benzene would come in between them. So you can easily like see a pattern. One component is forming certain kind of hydrogen bond or a dipole interaction, and to this we are adding a non-polar molecule, so that the non-polar molecule in coming between them and making them escape from the solution. Similar example is chloroform. Chloroform is having dipole moment, CCl4 is having no dipole moment. Okay, CCl4 toluene is a difficult case to remember in this case. Water and ethanol. Okay, water is forming hydrogen bond of itself, ethanol is forming hydrogen bonding of itself. When you mix them, both come, okay, in between them, and both of the hydrogen bonding between the similar molecules breaks, and both the components start escaping out. Okay, so this is easy to remember. Water ethanol. So if water methanol is there, water ethanol is there, water methanol would be there. Acetone carbon disulfide, acetone and ethanol. Okay, this is easy to remember. If I sincerely hope that you have not seen it, or fortunate enough to see it, or maybe you will be going to see in the college. When you go in any bar, okay, where you get drinks, hard drinks, so you will see that whenever someone orders a peg, say of 30 ml or say of 60 ml, then like some water is added or some soda is added to increase the volume. Okay, so what does the person who is making the peg does? Like someone orders say 30 ml of say 30 ml of ethyl alcohol, because drinking spirit is ethyl alcohol or ethanol. So he brings only 29 ml okay, and he add 30 ml water to it, okay, so still he would be forming 60 ml solution because that is a positive deviation solution, okay, because 29 ml of ethanol and 30 ml of water would form a solution whose volume will be greater than 59. Let us assume that it is 60. So a person who ordered for 60 ml, okay, 30 ml water and say 30 ml soda or 30 ml water with 30 ml ethanol, he is getting only 29 ml of alcohol. So this is how the bar people make a lot of profit, okay. So they give 1 or 2 ml alcohol less. So if they do it for say 1000 of customer per day, so they will be having 1 liter of alcohol as a spare which they can sell at another price, okay. So this is an example, okay. Hope you have written this now. So if you look at the graph of a positive deviation solution, okay, if we want to plot the pressure versus mole fraction graph, so XA was 1 over here, XA was 0 over here, so we know that XB would be 0 over here and XA would be 1 over here. Again we have assumed that suppose A is more volatile, so when XA is 1, so we will be having only one component, so the pressure corresponding to it would be P naught A, okay, because it is a pure component, and when we are at this point, that means XB is 1, XA is 0, so we will be having only one component, that is B, which is P naught B, okay. Now when they were following Raoult's law, we knew that this was the line for Raoult's law, okay. I will just make it on a dotted line for your easy understanding. So this was the Raoult's line, okay, when it was ideal solution. So this would be the variation of total pressure, okay. And if you look for the individual component, the variation of pressure of B would be something like this, and the variation of wave pressure of A would be something like this, okay. But we know that positive deviation solutions or real solutions does not obey the Raoult's law, so the total pressure would be greater than that of, okay, expected Raoult's law. So the graph of this looks something like this, okay. So this is the graph of the positive deviation solution. So you can see pressure is always greater than that of the total, okay, pressure is always greater than that of the total pressure. That was predicted from Raoult's law, okay. So you can clearly see that there would be a pressure maxima, okay, and the pressure would be greater than the pressure of the individual pure component. You can see the total pressure is always greater than the pressure due to pure component because the curve is obviously always above this line. So the total pressure is always greater than the pressure of the pure component, okay. And also we can say that there would be a pressure maxima when the solution shows a positive deviation, okay. We will study about what is this maxima and what exactly it is representing. So this would be the graph of solution showing positive deviation from Raoult's law. Hope this is clear to everyone. Just draw the graph quickly. Hope you are making the notes, because if you are making the notes, if you are sincerely following the lecture and noting everything, then it is very easy to understand and you won't find any difficulty in solving any of the questions, okay. Now let us look at another case, that is negative deviation from Raoult's law. Now again, what would happen in negative deviation? Obviously the word itself, now we can understand that negative deviation means that the total pressure over the solution is less than what expected from Raoult's law. So that would be the negative deviation, that means pressure has reduced, the total pressure over the solution has reduced. So negative solutions again do not obey Raoult's law, okay. Now what happens in a negative deviation solution is, suppose you are having component A and you are having component B, you are mixing them together. Now we say that when the interaction between A and B was less than that of AA or BB, then it was a positive deviation case. Now if the interaction between AB is much stronger than AA and BB, then we will say that it is a negative deviation, okay. So let me take an example so that you understand it in a better manner. So we are having say component A and component B. Initially in this only AA interaction was there, in this only BB interaction was there. Now when we mix them together, there would be AB interaction now. Now if AB interaction is very strong, Okay, if AB interaction is very strong, so what would happen? Neither this A will be able to escape out, neither this B will be able to escape out. So in that case, what would happen? Both the components are not able to escape out, so the pressure developed over the solution would be less than expected Raoult's law. Okay, less number of vapor would be formed. Now whenever the two components are forming strong bonds between themselves, then only negative deviation solutions are formed. So we'll say that in this case AB interaction is stronger than AA or BB interaction. Okay, hope this is clear to you. Now when we are adding these two components, because A and B have formed strong interaction between them, so we'll say that the molecules have come closer to each other, okay, have come closer to each other to form a bond. So we'll say that the solution has contracted. So if we are mixing 10 ml of A with 10 ml of B, okay, the final solution volume we are expecting it to be 20 ml, but because they have interacted, they have come closer to each other, so the solution will contract and the volume will be less than 20. So the volume mixing is less than 20. Okay. Similarly, because a bond is formed in this case. Now when you are mixing A and B component, A and B components are forming a bond. Now we know that whenever a chemical bond is formed, some stability is achieved and the energy is released out. Okay. So in this case, because a bond is formed, so energy will be released out. So we'll say that delta H mixing is less than 0. So we'll say that delta V mixing is less than 0. Okay, negative means less than 0. Delta H mixing will also be less than 0. Positive deviation mein, like positive means greater than 0. So delta V mix was greater than 0. Delta H mix was greater than 0. Okay. Delta G mix, we already know the formula would be less than 0 and delta H mix would be greater than 0. Okay, and we'll say that AB interactions is stronger than AA and BB or BB interactions, okay, due to which we'll say that escaping tendency of both A and B has decreased, of both A and B has decreased. Okay, hope this is clear to you. So we'll say that in this case, the partial pressure of A expected by the Raoult's law should be P naught A into XA, but this would be less than P naught A XA, okay, because the escaping tendency has decreased. PB would be less than P naught B into XB. So we'll say that the total pressure is also less than P naught A XA plus P naught B XB. Okay, so just write it down quickly. Hope this is clear to everyone. Again, very important theory questions can be framed on this, so don't neglect the theory. Like make a very proper notes, understand it, have a good reading. Like you can read a K.S. Verma book, Physical Chemistry by K.S. Verma, Volume 2. This chapter you can read it from there, and also after reading it, you have to read your NCERT as well. Okay. So I hope you have written this now. So if you look at this, AB attractive forces should be greater than AA and BB attractive forces. A and B have different shape, size and character. So if you look at the example, the most common example is acetone and chloroform. Okay, suppose we are taking acetone in one container and chloroform in the another. Now when we are mixing them together, so what happens? The hydrogen of chloroform and oxygen of acetone forms a hydrogen bonding. Now because of this hydrogen bonding, the two molecules come closer to each other and they have strong attractive forces, okay, and that's why we say that the escaping tendency of both the molecule would decrease and the vapor pressure would decrease. So all those components which are able to form strong hydrogen bond will be having negative deviation from Raoult's law. So we can remember this, okay. So we can say that acetone and chloroform, okay, water and HCl, okay. Similarly we can also say that water and HNO3, they can form hydrogen bond, because in HNO3 we are having oxygen, okay, and water we are having hydrogen attached to electronegative atom, so they can form hydrogen bonding. HCl, hydrogen, water is having hydrogen attached to oxygen, okay, and there is a electronegative atom chlorine. In generally we say that chlorine does not undergo hydrogen bonding, but we have already said in chemical bonding that there are some exceptional molecules in which hydrogen attached to the chlorine or the chlorine itself can undergo hydrogen bonding. Okay, so water and acetic acid. So example would be mixing water and acid, water HNO3, water HCl, water acetic acid. Okay, acetone and chloroform. This is acetone, this is chloroform. Acetone and aniline, same kind of interaction. Okay, aniline is basically NH2 with a benzene ring. Okay, and acetone is something like this. So you can understand, okay, they can form hydrogen bonding. Okay, so if you look closely with negative deviation and positive, you can differentiate very easily. In positive deviation, there was one interaction and the other molecule was not forming any new interaction. Rather, it was weakening the initial interaction. Okay, so acetone aniline, methanol acetic acid pyridine, chloroform and diethyl ether. Okay, hydrogen of chloroform can get hydrogen bonded to oxygen of ether, chloroform and benzene. Okay, so these are the few examples of negative deviation solution. Okay, so if you want to draw the graph, so because the solution is showing negative deviation, so if we are plotting vapor pressure along with mole fraction on the x-axis, okay, so if we say that partial pressure, vapor pressure of A is more than that of B, that is A is more volatile. Okay, so the Raoult's law was something like this. Okay, the total pressure of this would be less than the pressure of the pure component. So we can draw something like this. Okay, so this would be representing the total pressure. Okay, similarly, if you look for the individual component, for B this was the graph. Now for individual component the pressure has decreased. So this could be the graph for the individual components. Okay, but basically we are interested more in the total. Okay, so the individual partial pressure of this would also decrease. So if you are not drawing these also, only you are drawing this is also obvious. Okay, so this indicates the total one, this indicates the individual variation. Okay, so you can similarly draw this for the positive deviation as well. Okay, so in the positive deviation you could have shown that individual component pressure is increasing, so something like this, individual component pressure is increasing, so something like this. Okay, but I was drawing only for the total, so I hope this is not creating any ambiguity in your mind. Okay, so just draw the graph. So you can clearly see that there would be a minima in the pressure in this graph, the minima in the total pressure in this graph. Okay, and the total pressure would always be less than the pressure of the pure components. So just write it down quickly. Okay, hope this is clear to everyone now. Now a very important thing that which you study is azeotropes. Okay, before studying the azeotrope, let us study about distillation first. Okay, so we want to study the distillation of ideal solution. Okay, so everyone might be knowing the basic principle behind distillation. Distillation is basically carried out to separate two liquids of different melting point, of different boiling point rather. Okay, so suppose you are having say two liquids A and B mixed together forming a solution. We want to separate the solution into its pure component. So what we do, we start heating it. So we know that the component which was more volatile or which was having less boiling point would come outside. Okay, on boiling the vapor of that component would be formed first, which is having less boiling point. So one component would start forming the vapor. Okay, and we would condense it somewhere. So we'll get that as a pure component, and the second component which is having more boiling point would remain in the container. So this way we will be able to separate the two components. Okay, hope this is clear to you. So if you look for the ideal solution, so we have already drawn a graph for a temperature versus mole fraction graph. Okay, so let the graph, suppose this was your T naught B, that is boiling point of pure B. This is X is 1 over here, so it means that we are having only A component. So let the boiling point of A be T naught A, and here we know that XB was 0 and here it is 1. So we'll say that at this point only pure B is present, whose boiling point would be T naught B. So we know that the temperature mole fraction graph was something like this. Okay, hope this is clear. Okay, I've already told you how we are drawing this graph. So we know the basic fundamental of the graph. This was T naught A. Okay. Now suppose we want to distill A and B. Okay, distill the solution containing A and B. So what we are going to do, we are just going to boil this. Okay, so suppose we are at this composition A. Okay, so this represents, we know that this represents, lower temperature represents only liquid phase, higher temperature represents vapor state, the region between them represents both liquid and vapor state. So now when we start boiling the mixture, okay, we have taking a solution A whose mole fraction we can find just by dropping a perpendicular on the x-axis. So we will know the composition of this solution A. Now we have started boiling, so boiling means we have started increasing the temperature. So when we have increased the temperature, okay, let this point be over here. So when we have increased the temperature, say we have come to this point. So what would happen at this point? We know that, okay, at this point the first trace of vapor would be formed. Okay, so vapor would start forming at this point. So at point B we will say that vapor has formed. Okay, now what will be the composition of that vapor? Because this is the liquid curve, so the composition of vapor cannot be found out through this. So what we are going to do is we are going to drop a perpendicular on the vapor graph. The above graph was representing vapor. So this would be the composition. If you draw the perpendicular on the composition axis, you will get the composition of the vapor. Okay, hope this is clear to you. So when we started boiling the mixture whose composition was A, we reached to a point B where the first vapor would be formed. Now the composition of the vapor cannot be found out because this is representing a liquid curve. So for finding the composition of the vapor, we have to look at the vapor graph. So we are going to see the corresponding amount of vapor by dropping a perpendicular on the vapor, okay, curve. So we will get this point. Now the composition, okay, the composition with respect to this point would correspond to the composition of the vapor. So we can clearly see that the vapor is rich in A, okay, because the composition of A, the composition of vapor has moved towards vapor. Okay, you can clearly see that the mole fraction of A was increasing over here. So the component, the mole fraction of A in the vapor phase would be more. Okay, also logically you can say that because the boiling point of A is less than that of B. Okay, because the boiling point of A is less than that of B. So when you boil the mixture, so more vapor of A would be formed. Okay, now when you condense that, obviously you will get more liquid of A. Okay, so this is again a very important point. That component forms more vapor which is more volatile or which is having less boiling point. So again a very important factor. So you have to remember this, the mole fraction of that vapor would be more which is having less boiling point or more vapor pressure. Okay, so hope this is clear to you. So we started from point A, we moved to point B, the first trace of vapor would be formed. The composition of the vapor would be by just dropping the perpendicular on the vapor curve. So we got the composition over here, okay, of the vapor. So this would be the composition of the vapor. Now if we want to carry out the fractional distillation, okay, I hope you have studied this in your 11th class. Fractional distillation is basically doing the distillation over and over again through fractionating column. Okay, so we did the first round of distillation, so we got some vapor. Okay, now what we'll do, we'll condense that vapor. Now when we condense that vapor, suppose we reached a point C, this is again a liquid whose composition we know. Okay, so we'll get this. Now we'll again start boiling this. Okay, we again start boiling this. So we'll come to a point over here, the vapor would be formed. So that vapor composition would be somewhere over here. Okay, so you can see that we got pure A. So the vapor would be only in A now. Now when you condense that, you will get the liquid A. Okay, so I will repeat it again, this is a very important graph. So we are basically carrying out the fractional distillation. Fractional distillation is the process of distillation, like regular number of distillation we are carrying out till we separate the two components. So what we do over here, we start with certain composition of the liquid. Say we start from this point. So we start heating it, we come to a point B. where the vapors are formed, but we don't know the composition of the vapor because this represents the liquid line. So we drop a perpendicular on the vapor, so we'll get the composition of the vapor. So what we do over here, the vapor which we got, okay, we'll condense them. So we'll condense the vapor, so we'll get the liquid. So the vapor corresponding to this is condensed and we get the liquid C. Now this liquid C will have more of A and very small quantity of B, okay, because A was more volatile, okay, so A will have more vapor and B would have less vapor. So C would have more of A and very less amount of B. You can clearly see that we are moving towards this, towards the pure A. So the composition of A in the vapor state would be increasing. So we reached the point C, then we started boiling it again. So when we boiled it, we would reach at this point, okay, so this would correspond to another vapor composition. So we'll again condense it, okay. So if we get the pure A, then it's okay. If we didn't get the pure A, we'll again boil, we'll do it until we get the pure vapor, okay. So suppose you start with this point, okay, suppose we start with this point. Okay, suppose we start with this composition. Now we again started boiling it. So we reached a point B, okay, the vapor would be formed, but we don't know the composition of the vapor because this is the liquid line. So we'll drop a perpendicular on the vapor line. So this would correspond to the composition of the vapor. So we'll condense that vapor. So on condensing that vapor, say we get this composition. Okay, so all the vapor are condensed. So vapor will basically contain more of A and less of B, because you can clearly see that we are moving towards A. So the solution is containing more A and less B, okay. Now when we heat it again, so we reach a point over here, okay, the corresponding vapor would be something over here. So we again condensed it, so we got a point D, okay, we again heat it till the time we get the pure A. So this way we will be able to separate out A and B through fractional distillation. This can be carried out only for ideal solutions, okay. Now we'll say that in the condensate, okay, so in the condensate we'll have pure A, okay, and the residue, okay, so just see it over here. When we started heating, we reached a point A, that vapor would be formed, okay, vapor would be formed, we condensed the vapor, okay. Now what about the residue that was left? Because more amount of vapor of A was formed, we condensed it and we got another liquid, okay, but the initial liquid, because A formed the vapor and went out, so there would be more amount of B left in this, okay, so this is called the residue that is left over. So the composition of this would move over here, okay, because B would become, like the residue would become richer in the other liquid. If the vapor is rich in one component, the liquid would be rich in the other component, okay. A and B were both volatile, okay, out of which A was more volatile than B. So when we boiled it, so we got more vapor of A, still there was some vapor of B, but more vapor of A would be there, okay. So A went out more, okay, as vapor. So in the liquid remaining, we will have less of A and more of B. So we are saying that in the residue, the mole fraction of the other component increases. So we'll say that the mole fraction of, like mole fraction of the other component left in the residue would increase. So we'll say that it will start, the liquid will start moving towards this, okay, until it approaches the pure B. Hope this is clear to you. So when you boil, you get the first vapor, you condense that vapor, you get, okay, another liquid, then you again heat it, so you again form the vapor, you again condense it, so you reach over here, then you again hit it, then again you get it over here, you do it until you get the pure A. So in this way we will be landing at this point, okay. So we will be just doing like this. So this is going over here, heating, going over here, heating, going over here, heating, and then condensing, heating, condensing, heating, condensing, till we will reach the pure A, okay. So the condensate will have pure A, the residue which is left over there would be pure B. So we can carry out the fractional distillation of an ideal solution and we can get the two pure components. Hope this is clear to everyone. So again, a very important concept, easy to understand, okay. Now let us see what if we do it for a non-ideal solution or a real solution, okay. So we know that, let me first draw the graph, let me do the distillation process, you will understand what azeotropes are. So suppose we are doing it for the positive deviation solution. Okay, we know that positive deviation solution shows a maxima in the pressure versus composition graph. Okay, because the vapor pressure has increased, positive means it has increased. So the pressure versus temperature graph, we see that there is a maxima over there. So we say that this was the graph. Okay, so there is a maxima. So if we want to draw this graph on temperature versus composition graph, because pressure has attained maxima, so obviously the temperature would attain a minima. Hope this is clear to you. Okay, so in this case there would be a minima of the temperature. Okay, so again same way, suppose this was your pure A, the boiling point of pure A is T naught A, the boiling point of pure B is T naught B. Okay, so we know that because there was in positive deviation there is a maxima in the pressure. Okay, so there would be a minima in the temperature, because more is the pressure, okay, more is the vapor pressure, easily the liquid can convert into vapor. Okay, so the boiling point was less. If vapor pressure is less, so that means it requires a lot of heating. If it requires a lot of heating, that means boiling point is more, so that the vapor pressure becomes equal to the atmospheric pressure. So if the pressure is more, vapor pressure is more, the boiling point would be less. So there would be a minima in the composition versus temperature graph. Okay, so let me draw something like this. So this would be the graph. So you can see that there is a minima over this. So at higher temperature we know that liquid vapor state is stable, lower temperature liquid state is stable. Okay, so we got this point. Now I will tell you what this point is and what is the significance of this point. Okay, this point is basically your azeotrope. Okay, so I will just make you understand. So first let me draw the graph for the negative deviation as well. So if you look at the negative deviation graph, we know that for the pressure versus composition graph, okay, we were saying that there would be minima in the total vapor pressure. Okay, so we have already drawn the graph that the total vapor pressure would be less than that expected from the total vapor pressure predicted by Raoult's law. So there is a minima in the pressure. So because there is a minima in the pressure, so there should be a maxima in the temperature graph. Okay, minima is there, that means the vapor pressure has decreased. Okay, so we need to heat it more, so that vapor pressure becomes more, so that it becomes equal to the atmospheric pressure, so that it can boil off. So whenever the pressure is minimum, temperature would be maximum. So we know that at Xa is equals to 1, only pure component A was present, Xb equal to 1, pure component B was present. So because there is a maxima over here, so the graph of this would look something like this. Okay, so this would be the graph. At higher temperature, vapor is stable, at lower temperature, liquid stable. Between these regions is the liquid and vapor equilibrium. So this is your azeotropic point. Okay, so let us now come to the azeotropes. Now what are azeotropes? Now let me make you understand azeotrope by something like this. Suppose we are having two components A and B, we are heating it. Okay, now we know that one of the component will have higher boiling point and one of them will have lower boiling point. So basically the vapor would be more rich in the component whose boiling point was less. Okay, but suppose we have taken a mixture A and B whose boiling point was different. Individually their boiling point was different. We mixed it in a solution and then we heated it. Okay, now we analyze the vapor. If vapor had both A and B in equal proportion, that means that both of them has gone in the vapor state, and if we condense, they come back again in the liquid with the same composition. So that particular mixture is called as azeotropic mixture. So azeotropic mixture is a mixture of two liquids which has a constant boiling point and composition throughout the distillation. Okay. So this point is your azeotrope. P point is your azeotrope, because if you heat at this point, okay, if you heat till this point, we'll get the vapor. Okay, vapor will have the some concentration. Now when you condense it back, so the liquid will have the same, okay, concentration as that of the vapor. So this is called as an azeotrope. It behaves as a single liquid. So azeotrope is basically a mixture of two components, A and B, but at a particular concentration it is called as, if you look at this, at a particular concentration it has formed a azeotrope. So azeotrope is basically behaving as a single component. Now if you are having only say a component A, or say suppose you are having water, you boil this, you get the vapor of water, you condense it, you get the vapor of water. So whatever the concentration or whatever the amount of vapor was there, if you condense it back, you will get it in the liquid phase. So if you take the mixture of such compound and you heat it, we get the vapor. Okay, now when you condense the vapor, okay, now when you condense the vapor, we get the same concentration of the components that was there in the vapor phase in the liquid, then that is called as an azeotrope. So azeotrope is basically a constant boiling point mixture. So they are also referred as constant boiling point mixture. Okay, so let me explain through this, you will easily understand what I am talking about, then I will make you understand the definition again if you are facing any problem. So let us suppose we are starting the fractional distillation from say point A. Okay, so we have taken the solution whose composition is corresponding to A. Okay, so what we are doing, we have started to boil it. So we boiled it, we will reach a point over here. Okay, now when we condense, so basically it is a liquid line, so the composition of the vapor would be something over here. Okay, now when we condense it, we will get back the liquid, so we get back the liquid. Okay, so we get back the liquid XB, and again what we will do, we are doing the fractional distillation, so we will again heat it. So when we heat it, we will reach at this point, so it will correspond to some vapor, so we will reach at this point, then we will again condense, then we will again heat, so we will come at this point. Okay, now when we come at this point, we will condense. Okay, so we will get the liquid, we will heat, we will get again the same, okay, the same mixture, we will again heat, condense, so we will be stuck over here, we cannot move over here. Okay, so this is called as an azeotropic point or the azeotrope. So azeotrope is basically a constant boiling point mixture which is behaving as a single liquid. So when we are heating, so it is changing into the vapor without change in its concentration, or when we are distilling or when we are condensing it back, it comes back without the change in the concentration. So such mixtures are called as azeotrope. So we cannot separate these solutions because we will be stuck at this point. Now let us suppose we take this, okay, we start with this composition of A, we boil it, okay, so we will get vapor corresponding to say, because this graph is not drawn properly, so we will get something around over here, the vapor corresponding to this point. Now when we heat this, we will reach this point again, okay, we will condense, we will reach this point. Now when we reach this point, we condense, we heat, we condense, we heat, we will be stuck at this point, we will not be able to move over here because this is a azeotropic point, a constant boiling point mixture. So we will not be able to separate both the components through fractional distillation. So non-ideal solutions cannot be separated through a fractional distillation. So azeotrope is basically a constant boiling point mixture, okay, which has a constant composition throughout the distillation. So basically we will say that at this composition, okay, these two liquids A and B is forming an azeotrope. So azeotrope is like you have mixed two components but is behaving as a single component. So when you boil it, both the components are going in vapor, okay, when you condense it, both the components are coming back into the, okay, both the components are coming back in the container. When you again heat it, both the components are going in the vapor phase without change in their composition, and again when you condense, both of the phase are coming back in the liquid without change in the composition. So whenever you are doing that, so basically we are getting the two component without change in the composition as the vapor, and it is getting condensed and we are getting the same composition. So this is getting repeated, so it is basically acting as a single liquid, okay, because whenever we are having two components, so when you heat it, one component would be richer in liquid and one would be richer in the vapor. But in this case, both the components are going unchanged into the vapor state and they are coming unchanged or unchanged in their composition in the liquid state. So this is called as an azeotropic mixture. So azeotropic mixture is basically behaving as a single pure liquid. It is not behaving as if it was mixture of two liquids. It is behaving as if it was a single liquid. You boil, you get the vapor, you condense, you get back the liquid, you boil, you get the liquid, you get the vapor, you condense, you get back the liquid. So it is undergoing the change without change in its composition. So such liquids are called as azeotropes. But when you mix two liquid A and B, when you heat, we are expecting that one of the liquid will have, like one of the component has more boiling point, so it goes out as the vapor, and the other component will go in less amount as vapor and it will remain in the liquid. But in azeotrope, what will happen? Both of the component will equally go out without change in their composition, and again they will come back when they are condensed, okay, and when you again heat it, they will again go in the same ratio in the vapor state without change in the composition, they will again come back. So whatever the composition of the liquid is, the amount of the vapor, the composition of the vapor of the azeotrope is always same, okay. But while that of two liquids A and B, if you are heating, the composition of vapor and the composition of the liquid is always different. So azeotrope is such mixture of liquid that has a constant boiling point and composition throughout the distillation. So when you try to separate them through fractional distillation, so you can see that when we start with here, so we'll be stuck at, when we start from here, so the vapor will have this composition, we again condense, we again boil, we get the vapor, we again condense, we again boil, we'll get the vapor, we again condense, we again boil, we'll get the, so finally we will be coming at this point. Now when we come at this point, we condense, we boil, we condense, we boil, we'll getting the same composition of the vapor, so its composition won't be changing, so we won't be able to proceed further. So we'll not be able to separate the pure component, okay. Hope this is clear to you. Similar with this case, so if you start with this point, okay, I think you might have understood this now. So we'll say that they cannot be separated by fractional distillation, whereas ideal solutions can be separated by fractional distillation because there is no azeotropic point over here, okay. Hope this is clear to everyone. You can just draw the graph, okay. So we'll say that if we suppose start from this point, okay. So if we try to do the fractional distillation, so we are heating, we'll get the vapor, vapor will be corresponding to the vapor line, just condense it back, so we'll get the liquid, again heat it, we'll get the vapor corresponding to this point, again condense it, so we'll get the liquid, so again heat it, so after some point we'll reach to a point P. So in that case, we'll say that the condensate, if we start from here, will be a azeotrope, okay, and not a pure component, okay. And when we do a repetitive distillation at this point, it will always be going in vapor, coming back in liquid, going in vapor without coming back in liquid, without change in its composition. So the graph won't move it over here, okay. And residue, we know that, okay, because we are starting from here, so we have moved over to this point, so residue will be richer in B, okay. But we are not able to separate the two components through fractional distillation, okay. So fractional distillation cannot separate two separate non-ideal solutions because azeotropes are formed in it. Common example for a negative deviation azeotrope is, okay, for a positive deviation azeotrope is 5% by mass water plus 95% ethanol. So this is also called as rectified spirit, okay. So this is the example of positive solution, positive deviation solution. So this is also showing a azeotropic point at 5% by mass water and 95% by mass ethanol. For negative deviation, 20.25 mass percent HCl plus 79.75 mass percent water, okay, or 32% water and I think 68% HNO3. Okay, I'm not sure about this, so you can just escape. So I think it is 32% water and 68%, no, 32% HNO3 and 68% water. 32% by mass HNO3 and 68% by mass water will form a negative deviation. So we can understand that azeotropes are formed at a particular concentration. They are not formed at all concentrations. Okay. So I hope you have drawn these graphs. Okay, these graphs are very important, starting from here. Okay, the positive deviation graph, the negative deviation graph. Okay, and the ideal solution graph, temperature versus mole fraction graph, and then azeotropic graph. Okay, solution showing the negative deviation and the solution showing the positive deviation. Okay, positive deviation, there would be a minima in the boiling point or the minima in the temperature. In a negative deviation, there would be a maxima at the temperature graph, and that maxima point would be your azeotropic point. Okay. So we have understood that the boiling point of this azeotrope would be less than the boiling point of the two pure component, and the boiling point of this azeotrope formed at this point would be more than the boiling point of the pure component. Okay. So I hope we have already crossed the time, so we got engrossed in this concept that I missed to see the clock as well. So you have a scheduled next class as well. So I hope you have understood this. This is little tricky, this is little theoretical, but this is very important for your JEE Advanced as well as mains, as well as your local state competitive examinations. Direct questions are coming from here. So you need to know the properties of real solutions, examples of real solutions, similar with ideal solution, and the distillation graph and the pressure versus composition graph. Direct questions are coming from there. Okay. So I hope you have learned something new in this lecture today, and I hope you have enjoyed the session. We'll continue with the class on Monday. We'll be starting with the colligative property from Monday. Okay, I think there's some problem in DPP. I think you are getting the DPP today that has colligative properties. You can leave it for today. You can just revise the theory. You can just resolve all the DPP that has been given to you in this week. Monday we are going to start with another very interesting sessions and very interesting concept of colligative property. Okay, so this is it for today. I hope you have enjoyed it. If you have any doubt, you can just write it in the chat box so that I can get back to you